So the name of today's talk is Homotopical Categories. And model categories. But I wanted to start from some technical preliminaries from category theory and homotopy theory. And the first necessary evil that we'll have to overcome is set theoretical issues that arise when we try to localize categories. So I will start from from universes. The notion of a universe is quite important when we're dealing with such set theoretical issues. And so I will just quickly recap what it is and how one deals with them. So we start from the fact that, well, it's an axiom actually that any set belongs to, so first I will have to mention that the universe is just a set of sets, some kind of set of sets with some properties that I will describe. So any set belongs to some universe. And that's the key axiom here. And also let U be a universe. Then satisfies the following properties. So if X is an element of U and Y is an element of X, it implies that Y is also an element of U. So it's what's called the cumulative nature of universes. So if you have an element of this universe, it also is an element of a universe. Also, universes should be closed under basic set theoretic constructions. So if we have X and Y, two elements of a universe, it implies that the two elements set formed from X and Y also belongs to the universe. Another set theoretic construction which we need is taking a union of elements of a universe. So assume that A is an element of a universe, and for any I in A, X sub I also belongs to the universe. This implies that the union of all xi's is also an element of the universe. So another set theoretic operation that we need to perform is taking the power set. So if X belongs to U, it implies that the power set denoted P of X also belongs to U. Of course, this axiom implies that the universe cannot be an element of itself, because obviously that would yield the Russell type paradox. Another axiom is that the set of finite ordinals belongs to U. So it basically contains natural numbers. That's the point of this axiom. Another so yeah, those are axioms of the universe. And now I will list a few properties that can be easily deduced from them. So let me draw such a line, signifying that what is below just those are just corollaries of the axioms listed above. So besides this cumulativity that was established earlier as an axiom, we also have another flavor of it. So if we have a subset of an element of a universe, it implies that Y also belongs to U. Of course, this can be easily deduced from the fact that the power set belongs to the universe. So just a very quick explanation. So if X belongs to U, then U of X belongs to U. Then all its elements, including Y, also belongs to U. Also belong to U. Okay, so another statement which is dual to the one with the union of elements of a universe is that if we have an index set which belongs to the universe, and for each element of this index set, we have some element of a universe, then the product of all these sets also belongs to the universe. So another axiom is that the exponential also belongs to the universe, or if you will, the universe is Cartesian closed. Now, an important axiom, an important corollary states that the intersection of an arbitrary family of universes is a universe. And finally, if X is an element of a universe, this implies that X is a subset of a universe. The converse, of course, is not true. Okay, so note that the axiom star, which said that each set belongs to some universe, implies that first of all, universes exist. But moreover, each universe has a successor. So And the construction is pretty simple. We just take the intersection of all universes which contain U as an element. So it clearly differs from U because U cannot contain itself. And also, since we have this corollary number 9, an intersection of such family is also a universe. So we obtain a successor universe. Okay. So now we've introduced this sub-theoretical gadget. Now we can introduce category theoretic concepts related to universes. So basically, since universes are so well adapted to performing various set theoretical constructions, we can assume that objects and morphisms in a category belong to some universe, thus limiting the size of a category and allowing us to correctly perform certain constructions such as localization, taking functor categories, etc. So U categories, small U categories. Okay, so if U is a universe, then U category is a small category. Well, actually, not necessarily small, just a category C. A category C such that, first of all, each Hom set belongs to U, and the set of objects, so yeah, it's a small category, and the set of objects is a subset of U. A small U category is a U category such that its set of objects is not only a subset of U, but also an element of U. So each small U category is trivially a U category, but the converse is of course not true. So from the things described above, it follows that small U categories and functors between them form a U category. Okay, so what we have for U categories, we have the following. So have the following fact: each U category is a small U plus category, where U plus is the successor universe. This implies that U categories and functors between them form a small U plus category. Okay, so now we can discuss what we mean when we say small categories, locally small categories, and just categories. So we've introduced this notion of U category, and in this context, we redefine the usual notions of small and locally small categories to fit this description of smallness relative to a universe. Categories, locally small categories, and small categories. So a small category equals small U category. Oh, of course, we start from fits in some universe U. So locally small category is just a U category. When we're talking just about categories, then we mean U plus categories. Sorry, U plus small U plus category. So in the same vein, small set is the same as U set that is an element of U. And just set equals U plus set. Similarly, cat small means U category of small U categories. And cat large means U plus category of small U plus categories. So the passage to small U plus categories is a necessity because limits and colimits of U categories indexed by U categories are not necessarily U categories themselves, but maybe U plus categories, small U plus categories. Similarly, the functor categories between small u categories. Sorry, functor categories between u categories are not necessarily u categories, but also small u plus categories. Finally, the localization of u category with respect to some subcategory is a small u plus category, but not necessarily a u category itself. So let me just sum this up. So we need u plus categories to perform limits and colimits, take functor categories, and finally perform localization. So this is the reasoning behind the necessity for u plus categories. So it is reasonable to work with small u plus categories, and only sometimes remark that in fact we obtain after a certain construction we obtain a u category and not just a u plus category. Okay, so let me summarize what we have here. So we assume that each set belongs to some universe with certain properties of being closed. And so we define, so okay, each set belongs to some universe. We defined small u categories and u categories. We discovered that small u categories are more convenient because the functor category, for example, is once again so a functor category is also a small u category, and for any small u category and subcategory W, so yeah, for any small u category C and W, just a subcategory, there exists a localization with respect to W, which satisfies the universal property. So B of W is subcategory in isomorphisms of B. This implies existence, uniqueness of functor B gamma, which makes this triangle complete. So on the other hand, it is not true that if we replace small U categories with just U categories, we will have the same conclusions. So easily the prime category of between two U categories can be larger than a U category. Okay, so I think this is it for this set theoretical nonsense. And now we can do more homotopical stuff. So let me start from the notion of homotopical category. It is somewhat an abstraction of the notion of a model category because it only requires one class of morphisms instead of three. And so it is a bit more convenient. For example, when working with, I don't know, categories of chain complexes on an arbitrary abelian category, it is very easy to define what are weak equivalences, but it is not so easy to define what are fibrations or cofibrations. Okay, so let me introduce homotopical categories. So as usual, a homotopical category is a pair consisting of a category and subcategory, or if you will, W is just a class of morphisms for now. But as we will see, the requirements on this class forces it to be a subcategory. So what are the properties of W? Well, first of all, W should contain all identity maps. So the second is that it satisfies the property 2 for 6. So which states that for an arbitrary triple composable morphisms in C, such that the pairwise compositions belong to W, the remaining 4 morphisms also belong to W. So that's the property 2 for 6. It actually implies the property, sorry, 6 for 2. It actually implies the property 3 for 2. So, and the property 3 for 2 in turn implies the fact that W is a subcategory. So we already can see that it's not merely a class of morphisms, but actually a subcategory inside of C. Okay, so from properties 1 and 2, it follows that actually, sorry, properties 1 and 2 are equivalent to another 3 properties that can be required. So let me state them. So first, W contains all identity morphisms. So this is the same as the first property. The second property is the so-called condition of weak convertibility. So W satisfies condition convertibility. Which states that for any morphism S in C, such that it has left and right inverse with respect to W, it implies that S actually belongs to W. This in turn implies that all isomorphisms in C belong to W. Because, well, you just take the inverse of an isomorphism and you arrive to an identity morphism, which by assumption belongs to W. Okay, and finally, the third property is that W satisfies the 342 condition, which asserts that for any S and T such that they're composable if two the 3 maps from this. So here we have 3 maps. If two of them, any two of them, belong to W, then all 3 belong to W. Okay, so these are 2 sets of equivalent conditions on a homotopical category CW. And we say that 2 objects in a homotopical category in C are weakly equivalent if they can be linked by a chain of by zigzag of elements of double. So W is called homotopical structure on C. And we assume that any subcategory of C inherits a homotopical structure just by intersecting this subcategory with double. So we assume that in subcategory C is also homotopical category. We have the following homotopical structure. So we just take subcategory C prime inside of C, and we take the homotopical structure to be W prime, which is defined just like this. Okay, so we've defined homotopical categories. Now it's time to define morphisms between them, which are precisely homotopical functors. So if C, D are homotopical categories, then F from C to D is a homotopical functor. Better denoted with a small letter. Is a homotopical functor if it preserves weak equivalences. So if it takes weak equivalences inside of C to weak equivalences inside of D. So now let's consider a functor category between homotopical categories C and D. We say that natural transformation, I don't know, say tau is a natural weak equivalence if its components are weak equivalences, i.e. elements of double. So of course weak equivalences in D. So a homotopical structure on D induces a homotopical structure on the functor category from C to D. So if D is a homotopical category, Then the functor category is also a homotopical category. With weak equivalences given by natural weak equivalences. Analogously, a homotopical structure is inherited by the full subcategory consisting of homotopical functors. So let's denote subcategory consisting of homotopical functors. Then there's also a homotopical category. So analogously to the weak equivalence relation on the objects that was given for arbitrary homotopic categories, here we say that two functors are weakly equivalent if they can be connected by a zigzag of natural weak equivalences. So a homotopical functor f from C to D is called the homotopical equivalence. If it has a homotopical inverse such that their compositions are weakly equivalent to the identity of functors in a respective category. Okay, so now let me explain what is a deformational retraction of homotopical category. So if C prime inside of C is a subcategory, then we say that C prime is a right deformational retract of C if there is a right deformation of C onto C prime. Let me explain what this is. So what is the right deformation? This is a pair RS consisting of a homotopical functor from C to C prime and initial transformation S from the composition of the inclusion functor from C prime to C with this functor R. Now, obviously, a left deformation retract is defined just by inverting arrows. Okay, so now let's talk about the homotopic category of a homotopical category. So if C is a homotopical category, then by whole C or C square brackets, the subcategory of weak equivalence to the power of -1 is a category with the same set of objects as in C. And Hom sets defined by considering the zigzags of morphisms in C modulo certain equivalence relation, which I will describe right now. So with the same set of objects as in C, and with Hom sets consisting zigzags of maps C. So zigzags go obviously from X to Y, and each map in the opposite direction should be an element of W. So this does not look like X. That's better. So this should belong to W. Maps in C with opposite direction. And we should mod out by an equivalence relation generated by conditions of the following form. So obtained from F prime by removing identity morphisms. So F is obtained from F prime by composing two morphisms in the same direction. And finally, F is obtained by removing two coinciding morphisms going in the opposite direction. Okay, so we obtain a functor from the category C to the homotopical category of C, which is a localization and which acts on objects as identity. And which maps morphisms into zigzags which contain just one morphism. Such localization always exists, but it is not necessarily locally small. From the universal property of localization, we immediately derive the following corollaries. So, first of all, for any homotopical categories C and D, and any homotopical functor f from C to D, there exists a unique descent of this functor to homotopical categories. So let me, for simplicity, denote like this the category of your small homotopical categories, and for any homotopical functor between the two, there exists a unique homotopization of this functor, if you will, which goes between homotopical categories of this homotopic categories of this homotopical categories, such that it obviously fits into the following square diagram. So the same holds for natural transformations between two homotopical functors. So if we have two homotopical functors which go from C to D, and we have a natural transformation H between them, then there exists a unique natural transformations of functors between homotopical categories. This in particular implies that for any two homotopical functors between C and D, so we go the subcategory homotopical functors. We have and assume additionally that F1 is weakly equivalent to F2, then their homotopical versions are not just equivalent, but actually isomorphic functors between homotopic categories. So the direct corollary of this is that if we had a homotopical equivalence between two homotopical categories, then its homotopical version is an equivalence of categories. Okay, so let me finish this with mentioning one important property which we will establish for model categories. So homotopical, or basically any relative category, is saturated if the localization morphism inverts just a localization functor inverts just with equivalences. So the pre-image of isomorphisms in homotopic category coincides with a class of weak equivalences. And we have the following property that if a homotopical category is saturated, this implies that both the functor category and the subcategory consisting of homotopical functors are both saturated. It is actually a very simple exercise. Sorry, I'm not saying that it's a simple exercise, but it's an exercise to check this property. You just have to check it component-wise for actual transformations. Okay, so that was the part about homotopical categories and homotopical functors, and now I'm ready to go back to model categories to sort of explain how all this fits into the general context of homotopical categories. So as was explained on the during the first talk, a model category is just a small bicomplete category, locally small bicomplete category with three distinguished class morphisms, such that they satisfy certain axioms and let me briefly recap this. So M is a model category if has three classes maps with equivalences, cofibrations, and fibrations, denoted by this equivalence sign over an arrow, this kind of arrow, and two-headed arrow. So we have 5 axioms of model category. Which I will really quickly recall. So M should be bicomplete. Second axiom states that weak equivalences satisfy 642 property. The third axiom states that cofibrations and fibrations are closed under retracts. The fourth axiom states that we have two lifting properties. So cofibrations have the left lifting property with respect to trivial fibrations, and trivial cofibrations have the left lifting property with respect to all fibrations. And finally, we have the fifth axiom that states that for a morphism in a model category, there is a canonical factorization in 2 ways. Either it is a cofibration followed by trivial fibration, or it is a trivial cofibration followed by fibration. Now, have the following proposition. Actually, any model category with a subcategory of weak equivalences is a homotopical category. So So let me prove this. Actually, all that we need to establish is that all identity maps belong to the subcategory of weak equivalence. So everything else is covered by axioms of the model category. This, however, is easily established because we have a factorization of this map like this, where Q is a trivial fibration, and we have an identity which implies that the 3 for 2 property, which is a corollary of 6 for 2 property, implies that Q is actually a weak equivalence, which means that so by assumption, so by assumption, Q is a weak equivalence, and by 6 for 2 property, we see that the identity morphism of the object X is also a weak equivalence. Okay. So now we have to compare, well, we want to compare our definition of a model category with the definition of a closed model category in the sense of will. So let me just list the differences and what we have to show that in order to establish the fact that, in fact, every closed model category in the sense of equivalent is a model category in our sense. So well, of course, we have to assume beforehand that the versions of axioms 1 and 5, that is axiom about completeness and axiom about factorizations are given in the same way that we give them. So, of course, it's not true that every so initially Quillen defined model categories as categories which were closed only under finite limits. And of course, we can't expect any finitely closed, finitely complete category to be by complete. But if we assume that we have functorial factorization and categories are defined by complete, then the version of axioms due to equivalent is equivalent to axioms given input. So let me state the differences. So we have to check that, first of all, axioms from 1 to 5 imply that weak equivalences are closed under retracts. And that free for two property implies 6 for 2 property. Yeah. So yeah, so that's the second part. So it implies 6 for 2 property, obviously not in the general case, because 6 for 2 property is strictly stronger than 3 for 2 property, but on the assumption that we have axioms 1, 3, 4, 5, and weak equivalences are closed under retracts, i.e. the first point. So now we will prove the first point, and the second point will follow from the fact that model categories are saturated in the sense explained above. And this will be proven, I think, next time, but the proof will only use the axioms listed here and the condition that equivalences are closed under retracts. So let me prove the first point. That is that weak equivalences are closed under retracts. So we want to show that if X is a weak equivalence and A is a retract of X, then A is also a weak equivalence. In particular, we have the following diagram. Okay. So we will use the factorization axiom to enlarge our diagram in order to see the desired property. How we will do this? Well, we have, so first of all, let's assume that we have A here, A prime here, X here, X prime here, here once again A and A prime. We'll call this map P. This map will be called Q. And what we have here is that first of all, just write the top row of the diagram without any changes. Then we may, first of all, decompose A like this. So we have a cofibration followed by a trivial fibration. Then the functoriality implies the existence of map P to primes. And so we have, yes, here the map is called P prime Q prime. So we have the map A prime here, A2 primes here, map X here, map X2 primes here. The map Q2 primes is here. It also exists by functoriality. And we also decompose the map A prime in the following manner. So we have a trivial cofibration followed by just some fibration. Okay. So what we can say now? Well, we see that the composition A prime A2 primes is equal to A. The same with X's, and that the composition Q2 prime P2 prime is the identity map of A2 prime, also by functoriality of the factorization. Finally, the composition of R and J is here, is equal to A prime. This is all just the definitions of various maps. Now what we see is that 342 property and X being in weak equivalences imply that X prime, X prime, this is here, that X prime is also a weak equivalence. So the three maps X, X prime, and X2 primes satisfy the 342 property, and thus X prime is an element of weak equivalences. Now we use the lifting axiom, axiom number 4, to establish the fact that the map X prime, which is, as we established, a trivial cofibration, has in fact a lift right here, denoted by K. So we have K, which is a lift of X prime with respect to R. Now we observe that Rk is equal to Q2 primes, and that Kx prime is equal to JQ. This in turn implies that Rk multiplied by P2 primes on the right is the same as Q2 primes multiplied by P2 primes on the right, which is in turn, by factoriality, an identity map of A2 primes. This, and also we have that KP2 primes, A prime, is equal to K X prime P. Yeah. So this is the commutativity of so this so basically of this square, just of this square. So this in turn, by this observation, is equal to JQP, which is just J because QP is the identity map. Finally, observe that the identity map of A2 prime is a weak equivalence, and thus we may apply the property 642 to the pair A prime KP2 primes R to see that A prime and R belong to weak equivalences, and this in turn implies that A is a weak equivalence. So let's see how this works. So we've seen that that the pairwise compositions are KP2 primes is equal to the identity map of the object E2 primes, and also that KP 2 primes composed with A prime is equal to J, which is by assumption a trivial configuration. This in turn implies that the composition of all three maps, which is equal to wait a moment. Yes. So yeah. So the composition of all three. So actually, all that we needed to know was that A prime is a weak equivalence because A is decomposed as a prime followed by A2 primes, which is by assumption a weak equivalence. So the property of 342 guarantees that their composition, which is A, is also a weak equivalence. So we've proven this result. And we see that weak equivalences are closed under retracts. Now, we see that we have the following closure. We don't see quite yet, but we will prove right now that we have the following closure properties. So we have the following. Each pair of three classes of maps determines the third. So how we do this? Well, cofibrations are determined from fibrations and weak equivalences by taking all maps that satisfy the left lifting property with respect to the intersection of the two. So trivial fibrations are just the intersection of weak equivalences and fibrations. Fibrations are defined from weak equivalences and cofibrations. And cofibrations by taking the maps which have the right lifting property with respect to an intersection of cofibrations and weak equivalences. Finally, weak equivalences are defined by, so actually, so we can recover, for example, trivial fibrations by taking all the maps that have the right lifting property with respect to cofibrations. And we similarly recover trivial cofibrations by taking all the maps that have the left lifting property with respect to all fibrations. So weak equivalences in this context can be recovered by taking compositions of all trivial fibrations and trivial cofibrations. And this in turn implies that so this ability to recover fibrations, cofibrations, and weak equivalences implies that first subcategory spanned by cofibrations and trivial cofibrations give a subcategory which is closed under pushouts. Similarly, fibrations and trivial fibrations form a category closed under pullbacks. Okay, so let's prove the closure properties. They actually follow quite nicely from the factorization axiom. So let me do this real quick. So proof So let F be a morphism in a model category such that, for example, it has the left Ripken property with respect to fibrations. We would like to establish that it is in fact a trivial cofibration. Well, the reasonable thing to do is to decompose this morphism as a composition of a trivial cofibration followed by a fibration. And what we have, so we have the following diagram. And obviously we have a lift here by assumption. But now we observe that existence of this lift implies that F is in fact a retract of J. So let me draw this in more detail. So we have F here, we have this dotted arrow K here, we have trivial cofibration J here, and we have F once again here. So the composition of P and K by commutativity of the above diagram is just the identity map. And this in turn implies that since cofibrations and weak equivalences are closed under retracts, F is in fact a trivial cofibration. So this showed the second point. The first point is analogous. You just have to invert all the arrows. And the third point about weak equivalences being decomposed as a composition of trivial fibrations and trivial cofibrations, it just follows from the fifth axiom of model categories. So this is it. And now, in the remaining few minutes, I would like to give some very, very trivial examples of model categories. Those are not real life examples, but rather just artificial ones, so to speak. So, for example, if you have a model category M, then its opposite is also a model category. So cofibrations in this inverse category are just fibrations in the initial category. Fibrations are cofibrations, and weak equivalences are the same. So the second example is that of a comma category. So if we have an arbitrary object in a model category, then its under category and its over category are both model categories. So the model structure is induced by forgetful functor, which goes from, say, under category to the model category itself, and just says that the map is, say, cofibration if its image under the forgetful functor is a cofibration. Similarly, it's a weak equivalence if its image is a weak equivalence. So this functor U induces model structure. So any small product of model categories is a model category. You just define the classes of maps like component wise. So you say that the map is a cofibration if each component of this map that is an image under each projection belongs to a certain class. So so it's cofibration if each projection is a cofibration. So another example is that any bicomplete category admits the minimal model structure in which weak equivalences such as isomorphisms fibrations and cofibrations coincide, and they are just all morphisms. And also each bicomplete category admits maximal model structure, which may not be unique, as opposed to the minimal model structure. So bicomplete category needs a maximal model structure. In which weak equivalences coincide with all maps, and cofibrations are also consist of all maps in this category, and fibrations are just isomorphisms. We can do the same thing, but instead we can assume that cofibrations are in fact isomorphisms, and fibrations are all maps. However, there could be also other maximal model structures. For example, in set, there is a model structure where weak equivalences are just all maps, but where cofibrations are monomorphisms and fibrations are epimorphisms. Or you can do it in the different order. So say that fibrations are monomorphisms, cofibrations are epimorphisms. Okay, so that was an example of model category, of several model categories, in fact. Perhaps the most important here is this example of under or over category, because various properties of hunters can be explained in terms of these categories. Okay, so I think that is it for what I wanted to say today. Maybe there are some questions, suggestions, comments.